Okay, welcome calculus students. The purpose of this video is to demonstrate the use of a Riemann sum against a specific function, f of x equals x cubed. On the interval from 0 to 3, we're going to divide that interval into 6 equal subintervals, which means we're going to have essentially 6 rectangles, and we're going to use the right endpoint of each subinterval. And then one of the goals is to see if we can generalize the brute force method that we're going to use first, using summation notation and some of the theorems on finding the summation of, like, from I equals 1 to n of I cubed, for example. Over here to the right, I have pictured here's y cubed and x cubed in the purple, and on the interval from 0 to 3. This picture shows the interval from 0 to 3 being divided into 3 subintervals. And essentially what we're trying to do is find the area of each rectangle by using the right-hand endpoint of each rectangle to calculate the height of the rectangle by substituting this x value into the function to get the height. So for example, this height would be 1. This width would also be 1, because in this case each subinterval has the length of 1. This would still be 1, but for this x value substituted into x cubed, the height would be 8. So the area of that rectangle would be 16. What I mean by brute force is we're just going to actually do the hardcore calculation and see what number we come up with. But I do want to go to the Desmos graphing calculator and show you, give you a better idea of what's happening here. Here's the function f of x equals x cubed. On the interval from 0 to 3, I've broken it apart into 6 triangles, all with the same width, which is 1/2. To calculate that equal width, we say that we're going to take 3 minus 0, which is the length of the total interval, divided by 6, which gives us 1/2. So each subinterval is going to have a length of 1/2. And if we add up the areas of each of these rectangles, we'll get something that kind of sort of approximates the area under the curve. Now as we increase n, increase the number of rectangles to, let's say, 10, you can see that perhaps we're getting closer and closer to the true area. And this integral here, this summation notation, actually estimates the area under the curve, 24.5025. It's an estimate. If I increase the number of rectangles to 100, well, you can see that the rectangles are getting very, very small in width, and we're getting closer and closer to actually approximating what we call the area under the curve, or in this case, x cubed. So we're going to go back to here, calculate by brute force the area of those 6 rectangles that are pictured here. We should get this number right here, 27.5625. And then we're going to see if we can generalize that formula using summation notation. And finally, we're going to see what happens if we let the number of rectangles, or the n, approach infinity. Can we actually get the true area under that curve from 0 to 3? So here I've pictured taking the subinterval, or the interval from 0 to 3, into 6 equal subintervals. Again, I calculated that by, we think of this as A, and this is B over here. So 3 minus 0 gives us the distance between the endpoints divided by 6 will give us the width of each equal subinterval, so 1/2. Okay. Now that means that, and since I'm using the right-hand endpoint, I'm using these points right here. These are the values that are going to be substituted into the function to give us the height of each of the 6 rectangles. One of the things we'd like to come up with is a way to generalize how to determine the value of each of these x1, sub 2, sub 3, sub 4, sub 5, sub 6, so that we can substitute that into some summation notation. In other words, I want to take from I equals 1 to 6, and I'd like to have a formula here that applies to every area that I'm calculating, so that I can use summation notation instead of this brute force method. So what's happening here is that to calculate the x value that I'm going to substitute in here, you can picture starting at 0, and to get to the first x value, I'm traveling 1 width. That's what I mean here by 1 times 1/2. To get to the second sub x value, I am starting at 0 and traveling 2 widths. And I think you can probably figure out that to get to the third x value, I'll start at 0 and travel 3 widths, which is 3/2. So that's the number that I'm going to substitute into the function to get the height of the rectangle. So here I'm talking about calculating the area of rectangle number 1. Its width is 1/2. Its height is f of x sub 1, which means I'm taking 1/2 times x sub 1 cubed, because that's the function. F of x equals x cubed. So 1/2 times x sub 1 is 1/2. 1/2 cubed is 1/8. 1/2 times 1/8 is 1/16. Similarly, for the second rectangle, I'm taking the width of that rectangle times f of x sub 2, but x sub 2 is really just the number 1. 2 times 1/2. 1 cubed is 1. 1 times 1/2 is 1/2, but I wrote it as 8/16. Okay, and if I do r sub 3, the area of the third rectangle, I'm going to take 1/2 times f of x sub 3, but x sub 3 is 3/2. So I want 3/2 cubed, and that represents the height of the rectangle times the width of the rectangle. So that's really 1/2 of 3 cubed is 27. 2 cubed is 8. So the area of the third rectangle is 27/16. Now I'm going to eventually pause the video and come back and fill in the areas of the other 3 rectangles. But first I want to talk about how we generalize x sub I, x. If I talk about x sub I, I'm talking about what is the x value that I'm going to substitute into the function in order to calculate the height. Well, you can see x sub 1 is 1 times 1/2, x sub 2 is 2 times 1/2, x sub 3 is 3 times 1/2. Guess what x sub I is? I times 1/2. Of course, we would normally just write that as I over 2. Okay, so using summation notation, how can I represent the area of each rectangle? Well, I can take the width, which is constant, in this case 1 over 2 times x sub I, which is I over 2 cubed. That expression represents the sum of the areas of all 6 rectangles that are pictured over here. Now I'm going to pause the video and fill in the rest of these, and we'll see what we get for the sum of those areas using brute force. Okay, welcome back. I filled in the areas of the rest of the rectangles and then calculated the sum over here. Looks kind of messy, kind of like what I would have done on scratch paper. But I figured out that for rectangle 4, we would be taking half of 2 cubed, which is 4, but that's 64/16, so I pulled that over here. And rectangle 5 is 125/16. There we go. And rectangle 6 is really 27 halves, which is 216/16. If you add all these areas together, this is your total area of those rectangles, 441/16. And if I go back to Desmos, you can see that I proved that 441/16 is the same value as what we get by approximating the area under the curve using this summation. Now we're going to see if we can generalize this thing right here. And to do that, I'm going to go on to another page, and I'm going to suggest that I would like to look at what is the sum from I equals 1 to 6. Well, that didn't work out too well. Of 1/2 times I over 2 cubed. Now, of course, we could just put 1 in for I, 2 in for I, 3, 4, 5, 6, which is essentially what we did on the first page, but I want to see if I can come up with another way to do this. And the formula that you need to know in order to do this, there's a bunch of these, but one of the ones that is maybe not quite as well known is that if you want the sum from 1 to n, I equals 1 to n of I cubed, using mathematical induction, you can prove that that sum is represented by n times n plus 1 over 2, the quantity squared. As an example, if you want to sum 1 cubed plus 2 cubed plus 3 cubed, we should get 27 plus 8 plus 1, 36, I guess. So from I equals 1 to 3, we'd put 3 in for n. So that would be 3 times 4 divided by 2, the quantity squared. 2 into 4 is 2, 2 times 3 is 6, 6 squared is 36. Okay, so that is an example of the formula working. Now, using some theorems on what you can do with summation notation, well, let's first of all rewrite this part as I cubed over 8 times a half. That's really I cubed over 16, or 1/16 of I cubed. So there's a theorem about summation notation that says I can pull that constant out and do the sum from I equals 1 to 6 of I cubed. But we just said that a way to calculate this sum is to put 6 into this formula right here. So that would be, well, 6 times 7 divided by 2, the quantity squared. 2 into 6 is 3. 3 times 7 is 21. I wonder what 21 squared will be. 1, 2, 2, 4. No real surprise there, 441. So this becomes 1/16 of 441, or 441 over 16, which is exactly what we got using brute force. So now I'm going to ask the question, what if we change this 6 to an n? Can we come up with a general formula for evaluating the sum of those rectangles when n is an arbitrary number of our choice? So I'm going to go to another page, and we're going to examine what happens if I take the sum from I equals 1 to n of, well, now we got to think, what is the length of each subinterval when there's n rectangles? It's 3 minus 0 over n. The length of the entire interval is 3. We're dividing it into n equal subintervals, so 3 over n represents the width of each subinterval. Now I need to come up with an expression for, like, x sub I, the right-hand endpoint of each subinterval that I'm going to plug into the function. Well, for the ith subinterval, I've added on I of these widths. So the value of this x sub I is really I times 3 over n, or 3i over n. That's the value that I'm plugging into the function, which is f of x cubed. So I want to see where this leads us to see if we can come up with a general formula that doesn't include summation notation. So if I, not a very good looking I equals 1 to n, what does this become? It becomes 27i cubed that's supposed to be a times symbol. 27i cubed over n cubed. Remember, n is just a constant, so I'm going to simplify this to I equals 1 to n of 81 I cubed over n to the 4th. And now I can pull this constant out front, 81 n to the 4th. And I've got the sum from I equals 1 to n of I cubed. Oh, but guess what? I cubed is that well, I'll write it this way. N times n plus 1. That's right parentheses over 2, the quantity squared. So using, well, I'll go ahead and just simplify this. This will be n squared plus n, the quantity squared. Squaring a binomial gives us n to the 4th plus 2n cubed plus n squared over 4. Okay, so I'm going to write this as 81/4 times n to the 4th plus 2n cubed plus n squared over n to the 4th. And now I'm going to separate this into 3 separate fractions. Move up here in red. I'll have 81/4 times, well, let me put it in parentheses, n to the 4th over n to the 4th is 1. 2n cubed over n to the 4th is 2 over n. And n, that's an n cubed. Or no, that's an n squared, sorry. N squared over n to the 4th is plus 1 over n squared. So there's our general formula for the area under x cubed when we're dividing the interval from 0 to 3 into n rectangles. Now, when n equals 6, I should be able to plug 6 into this formula and get that 441 over 16, right? 81/4 times, when I put a 6 in here, I get 36. So I'm going to convert everything to 36 while I'm at it. 36 over 36 for 1 plus 2 over 6 is the same as 1/3 or 12/36 plus 1 over 6 squared is 1/36. So it looks to me like I got 36, 46, 40, 49/36. 81/4 times, what did I say, 49/36? 46, 48, 49/36. Let's see, I think 6 divides into, pause the video a second. Yeah, I just had to pause there for a second. These are both divisible by 9. So this becomes a 4. This becomes a 9. When I multiply these values together, I get, well, 9 times 49. I'm guessing that's going to be 441. But I do get 16 in the denominator. 9 times 9 is 81. Carry the 8. 36 plus 8 is 440. 44 rather. And there it is. So the fact is, if I want to know what 100 rectangles are going to evaluate to, I would put 100 in here for n. If I want to know what the value would be if I put 1,000,000 rectangles, I'd put 1,000,000 in for n. And so that leads to the question, what happens if we take the limit of this thing as n approaches infinity? The limit as n approaches infinity of the sum from I equals 1 to n of 81I cubed over n to the fourth. Well, we just saw that another way to write this summation is this thing right here. And what happens to this expression as n approaches infinity? What is the limit of this expression as n approaches infinity? The fact is that when n approaches infinity, this fraction approaches 0, and this fraction approaches 0. So the limit of this sum as n approaches infinity is 81 fourths times 1 plus 0, which is just 81 fourths. Okay. Now, assuming that you already know how to take the definite integral from 0 to 3 of x cubed dx, guess what? Antiderivative is 1/4 x to the fourth, evaluated from 0 to 3, equals 81 fourths. So really, a definite integral is really just the limit of a Riemann sum. That's why your calculus books, before you start talking about definite integrals, introduce you to Riemann sums and limits and all that stuff, so that you can see where the definition for a definite integral came from, and the fundamental theorem of calculus, proving part 1 and 2 of the fundamental theorem of calculus is based on this definition for a Riemann sum. It's a limit as n approaches infinity of a Riemann sum. We'll go back to here. I'll change n to 100 one more time. We'll see that we've got 20.65705 and 81 fourths is 20.25. So we're at this point just a little over 4 100ths, or no, 20.25, 4/10ths from having the correct area. Increase that to 1,000 rectangles, who knows? We might be very close. Okay, end of video. Hope you got something from that.